all of the important information, notice that the important information or all important information, let's say, is found or is given by the leading entries in the row echelon form of the row echelon form, right? Of the matrix. Yeah. So, question. How many basis vectors will there be for the row space? The number of rows with leading entries. How many basis vectors will there be for the column space? The number of columns corresponding to columns with leading entries. Also the number of columns with leading entries. So in this case, like, let's see this, right? How many basis vectors do we spot for the column space? 3, because there are 3 columns with leading entries. How many basis vectors for the row space? 3, because there are 3 rows with leading entries. So what can we automatically notice? The dimension, the number of basis vectors for the row space of a matrix is the same as the number of basis vectors for the column space of a matrix. And what is this number? Can anyone tell me? What is the number of row space vectors? The number of column spaces vectors? It's just the number of, exactly, leading entries. All right, so the dimension of a matrix is the number of leading entries, or the dimension of a row space, and the dimension of the column space is just the number of leading entries in the row echelon form. So let's start this with a new page. The dimension of the row space and the column space is just the number of leading entries. Let's give that a name. The shared dimension, so the same dimension, right? So the shared dimension of row A and column A, that is to say the row space and the column space of A, is the rank of A, denoted by rank A. So the rank of a matrix is just the dimension of the row space, column space. What is the rank? It's just the dimension of the row space, column space. We already know what to count. We're just counting the number of leading entries in the row echelon form of A. Easy. That's it. Okay, question. What is the rank of A? Oh, there are 3 leading entries, or equivalently 3 column basis vectors, or column space basis vectors, 3 row space basis vectors. So the rank of A in this case is 3, right? So we're literally just counting the number of leading entries in the row echelon form. So technically speaking, I could have defined rank all the way back in week 1. I could have said, let A be a matrix, count the number of leading entries in the row echelon form. That's the rank. So now we're just defining it relative to row space and column space. All right. So here's a question. What is the maximum possible rank? What is the largest possible rank of an m by n matrix? Right. So let's take an easy sort of example. If my matrix were 2 by 3, what is the largest possible rank? Well, how many leading entries at most can I have in a row echelon form? In this case, just 2, right? Because I can't possibly have another leading entry. There are only 2 rows. If my matrix were 3 by 2, what is the maximum? Has it become 3 now? Oh, so this is 2 by 3. The maximum possible rank is 2. This is 3 by 2. What is the maximum rank in this case? If I have a leading entry here and a leading entry here, can I still have a leading entry in the 3rd row? No, I'm going to have to clean that up at some point. So it's still 2. So, we are limited by the number of rows or columns. It's the lesser of m or n, right? So what is the maximum possible rank? The rank of a matrix A is going to be, at most, the minimum, the lesser of m and n. So minimum, the smallest possible value between m and n. Yes. Okay. In the special case where I have maximum rank, so if the rank of A is equal to that maximum, which is the smaller of m and n, then we say that A is of full rank. So just a special term to describe a matrix with the largest possible rank, we say that it's full rank. All right. Any questions? No? So y'all should be asking something now, like there's something we haven't, oh, maybe let's just copy that. We've already, actually, is it still here? Would it be, yes, very nice. Well, let's just put that here. This is the previous matrix that we saw, right? We just explored the row space, column space. I've circled the 3 leading entries. So let's just write it out. In this case, the rank of A is just count the number of leading entries, 3. And if I really want to check, this has to be equal to the dimension of the row space of A, as well as the dimension of the column space of A. They're both 3. Okay. Now, let's spice it up. Question. There's something we haven't seen since the start of class. I introduced the null space and we're like, yeah, we already know what the null space is, we know how to solve it. So I'm going to ask, what is the dimension of the null space? So let's just do a quick recap. What is the null space, again, of a matrix? The null space of a matrix is, so recall, the null space of the matrix is what happens when you solve AX equals 0. So if we wanted to do the null space, you would imagine that maybe there's a 0, 0, 0, 0 here, and then we would solve. Right? So if we were to solve, how many solutions would this have? We would assign arbitrary parameters to non-pivot columns, columns without leading entries. Let's say we assign parameters to columns 2 and 4, right? So every solution in the null space is going to be S, let's say that's one of the parameters, plus T times one of the parameters, where S and T are any real number, right? So we would say, okay, we know how to do that. We're just solving a homogeneous system. So let's assign parameters there. We're like, okay, S, let this be T, and then I can construct. So how many vectors do I need to create the null space? Notice that I haven't actually solved. I'm just looking at the matrix. Is it the number of columns that I assigned parameters to? Right? It's the number of columns that have arbitrary parameters, because that's going to tell me how many vectors I need to split up in constructing the solution. So in this case, the dimension, let's use blue, of the null space of A is 2. because this is the number of columns that we assign parameters to. Assign parameters, columns without leading entries, let's say. And what that means is this is where we assign arbitrary parameters. Right? So I'm just going to give that a name, just a new name, the dimension of the null space. It's called the nullity. Longer name, nullity of A. Okay, so the nullity of A is the dimension of the null space. This is just going to be, so we can conclude in this case that the nullity of matrix is 2. Do you mind explaining why it's only the columns without leading entries and not all the columns? Well, what we're doing is we're solving a homogeneous system, right? And if we solve a homogeneous system, what we do is we assign arbitrary parameters, and then that gives us our solution. So in this case, we are assigning 2 arbitrary parameters, and our solution would be S, so maybe an expression involving S, and maybe sometimes T as well, S and T, et cetera, right? And then when we split that up, that's going to be S times something plus T times something. So 2 vectors. Every solution is a combination of those 2 vectors. That is to say, for each of my arbitrary parameters, I can associate with it one sort of set of vectors that form solutions to my homogeneous system. Right.
So what you mean is it because S and T forms the rest of the vectors, so they are so-called form the rest of the solutions. So
yes, right. So all of the solutions are just combinations of S times something plus T times something. So those 2 somethings will form all of my solutions.
Okay.
So those 2 somethings form a basis for my solution set. Dimension is 2.
Understood. Thank you.
Yep, no worries. Okay, so the dimension of the row space column space is rank. It's just count the number of leading entries in a row echelon form. The dimension of the null space is called the nullity. Do I have to find the null space to find the nullity? Or is there something I can just count quickly so that I find the nullity? Notice that in this problem, we didn't really have to solve the homogeneous system. We just counted some. What did we count? A very nice result. Waiter is saying, max rank minus LE. I'll give you something that doesn't even require calculation first. The nullity of a matrix is just the number of columns without leading entries, right? We're just counting how many columns there are no leading entries, right? So be careful. It might be tempting. Oh, do we look at the columns or rows without leading entries? Well, we assign parameters to columns. Sorry. So we're counting the number of columns without leading entries. Okay. Questions? So to end today, just one final result to end today's class. Oops, sorry. Oh. Just erase this. Right. What's one thing that we can do to end today's class? Let's just take a look at the rank and the nullity. So let's do a quick recap. What we did today was we explored the fundamental spaces, of which there are 3. Right? We have the row space, the column space, and the null space. We found bases for each of these fundamental spaces, but we also talked about their dimensions, in particular, the rank and the nullity of a matrix. So we're now generating subspaces out of just a matrix, right? An easy way to find the rank is to just compute the number of leading entries in a row echelon form of A. Easy way to compute the nullity is the number of columns that we assign parameters to, number of columns without leading entries in the row echelon form of A. So what does that tell me about the rank and the nullity? Rank counts number of leading entries. Nullity counts columns without leading entries. So final result, our big result for today, theorem 6. This is called your rank nullity theorem. The rank nullity theorem states that if A is an m by n matrix, then the rank of A plus the nullity of A is equal to, well, what am I counting for rank? Number of leading entries in a row echelon form. Nullity, I'm counting number of columns without leading entries in row echelon form. Number of leading entries plus number of columns without leading entries is the total number of columns. So if A is an m by n matrix, the rank of A plus the nullity of A is just n. That is to say, the sum is the total number of columns. Okay. Surprisingly large result that has a very surprisingly simple explanation. Right? It's just a matter of counting leading entries. Are there any questions about the rank nullity theorem? None? All right. Thankfully, we have a bit of time, so I won't end, I'll end a little bit earlier, but just to tie together today's discussion, I want to go through there's a question. Is there a difference between counting the leading entries in rows instead of columns? Well, they're the same, right? If I'm counting leading entries, rows with leading entries is the same as columns with leading entries. But if I'm counting non-leading entries, the only reason I care about the columns is because that's where I assign my parameters. I can count the rows without leading entries. In this case, for example, here, right? There's one row without a leading entry, but that doesn't really give me any information about solving a homogeneous system. When I solve a homogeneous system, what I really want to find are the columns without leading entries. All right? Does that make sense? So to end today officially.
Do you mind explaining the non-leading entries but in the columns?
Right. I mean, why are we looking at the columns? Because we're solving a linear system. Right? The only reason we're looking at the columns is because the null space is a solution set of a homogeneous system. Okay. Right? If we solve a system, we're not going to look at the rows, we look at the columns. Right? So there's no point looking at the rows, basically. Yeah.
Oh, okay. I think that's my point. Thank you.
Anyways, okay. To end, let's just do something fun. Theorem 7. Let's revisit our equivalent statements. Part 3. Or no, this is already part 4. This is our 4th version of the equivalent statements. And today we end up having 18. We're so close to the end. There are 20. I promise you guys 20, but today we finish up until 18. Okay, equivalent statements. The following are equivalent. For an n by n matrix A, we already know the first A is non-singular. Second, A inverse exists. We've already heard this so many times. That means if I solve AX equals B, it has a unique solution given by A inverse B, for no matter what B is. In a special case where B is a zero vector, I only have the trivial solution, which means if I row reduce A to its reduced row echelon form, I have the identity matrix, which means A is a product of elementary matrices. So the capital pi means product. And so the determinant of A, the product of that determinant, the determinant of the product is non-zero. What did we add last time? Last time, we said that, oh, because AX equals B is consistent, the columns of A can create any B in Rn. So the columns of A, the span of the columns of A is Rn. Next, we also said that the columns of A have to be linearly independent because they only have the trivial solution from statement form. If I have a set that spans and at the same time is linearly independent, the columns of A form a basis for Rn. And because A and A transpose are both invertible, those three statements on columns apply to rows as well. 11, 12, 13. The span of the rows is Rn. The rows of A are linearly independent, and the rows of A form a basis for Rn. All right, now let's add. The span of the columns of A is equal to Rn. We now have a new name for the span of the columns. That is just the column space, right? So statement 14, the column space of A is just a restatement of statement 8, right? Statement 8. Statement 14, the column space of A is all of Rn. 15 is going to be a restatement of 11. 11 says the span of the rows is Rn. We already have a name for the span of the rows. That's just the row space of A is Rn. Statement 16 is going to be a restatement of 4. 4 says that the homogeneous system has only the trivial solution. That means the null space, the solution set of the homogeneous system, has only the trivial solution. That's just the zero space. There's only one solution, which is the trivial solution. From 14 and 15, the dimension of the column space and the row space is Rn. That is to say, the rank of A is n, or A is a full rank. And from 16, what is the nullity of A? It's the dimension of the zero space, 0. 1, 2, 3, 4, 5 new additions. The next addition happens next week, and then the last addition happens the week after. All right. That's it. Equivalent statements. Are there any questions about today's class? What's for tutorial 5? Oh yeah, I'm not sure if you all received my email because I sent it using the automatic luminous. So it should have sent you guys an email blast, but if it didn't. So first of all, the fundamental spaces, the guide has already been uploaded and you can already solve these problems. And for the tutorial, I had to retype one of the tutorial problems because there was a typo. Tutorial 6 is this. It's going to be about bases and dimension. Can you give us the assignment? Are there info regarding the finals? I think I sent that out at the beginning of this semester at the housekeeping document. Let's just see the finals. April 20, Tuesday, 1 to 4 p.m. That's most likely going to be online. So it's not, I'm not sure, but like I'm like 95% sure that's going to be online, because I don't think COVID's going to be settled by the 20th of April. Yeah. So this is from the housekeeping document, the start of business. Okay, no worries. Can you give us the assignment earlier? I don't think I can. I can ask the coordinator, but we'll see. Okay, but yeah, for now that's it. This is the fundamental spaces. Very straightforward lecture today. Next week is really, actually, we're technically speaking, we're done with all of the things we need to know. The next 3-4 weeks are all just applications of everything that we've done so far, right? So next week is really when we have sort of fun with what we're learning. A lot of drawing next week, which is kind of tough, but should be good. All right, any questions about today's class? Okay, so that is it for today. Don't forget to please download the new tutorial set that has the typos edited. That's been uploaded already. That's the new file on the shared file. We do tutorial 6 this week, okay? And I deliberately move things to make it shorter so that you have time to work on the assessment with me. But otherwise, yeah, I'll hang back a bit for questions. I have another class after this, so I might end the call in maybe 10 minutes. But otherwise, I'll see you guys on Friday. Yeah. No worries. You're welcome. Yeah.
Sorry, can I ask, like just now you mentioned about the